Tomorrow's Wednesday. I will not be here. You will pass back the Unit 2 papers. Then you will watch 30 minutes of a movie for questions number 60 to 64, which are part of assignment 9.1, and that's not written on the study guide, so it's 60 to 64. Yes, Dejo? Throw it at someone. I think Hugo, the appropriate recipient for your
really terrible.
Funk Joe. Well, if it was especially dangerous, we would know. You could rinse that outside with our.
Okay. It says it doesn't. I don't know anything about the potassium iodine.
It's supposed to be bad for your hands.
Yeah.
I said push it down the drain.
Just drink it. It's a good idea. Just drink something.
Next. After watching that movie, you'll have like 10 or 20 minutes to work with your groups on your solar house models. You probably would not have enough time to like bring stuff to build, but you might have enough time to meet and chat and plan. So bring your solar house model notes, talk materials. Let's wrap up this climate change, shall we? And I realize I need to make a little shift in my teaching strategy. Because pretty much the days of high school kids objecting to climate science are probably over, aren't they? Like, you don't have to like point at anybody, but honestly, how many kids in the room do you think deny the existence of climate change? Maybe one? Like I said, we don't need to single anybody out, but honestly, like I'm okay with this, but like how many? Like maybe one kid or two kids? Maybe? If any, right? Maybe none? Sam does. So, like I said, I don't really care if somebody, but I think that argument's kind of done now. I don't think it's actually an argument worth arguing anymore. So I want to wrap up the climate science. Look up at the screen. Did everybody see this slide? Yeah? I show you the way that he did his science experiments back in the day. Then I show you the accumulation of curves, not just carbon. And so please look up. Remember that humans are adding a variety of gases. I don't know how much I discussed this yesterday, but please look up. A lot of our man-made global warming comes from a group of chemicals that are entirely artificial, just added by humans. A lot of times we talk about the CO2, but about half of our global warming is other stuff, and about a quarter of our global warming is this really weird stuff. Did we talk about those yesterday?
Yes.
Yes? Did I remind everybody that CFC is not a chemical formula, that's an abbreviation? An acronym? Did we go over where these come from? You may want to scribble this into your notes. CO2 comes primarily from fossil fuel energy, like transportation and electricity. But we get some CO2 from deforestation and farming. Because like things decompose on the surface, so aerobic decomposition makes CO2. Then, we get methane from any aerobic decomposition, like landfills, like... What?
Don't you mean anaerobic?
What did I say?
Aerobic.
Dang it, I meant anaerobic decomposition. Like landfills. Methane comes from anaerobic decomposition. Yeah, Hugo?
Why is that anaerobic decomposition in landfills? Does that mean that there's no oxygen?
That's what it means, because you're underground.
Oh, and
Yeah. When you bury stuff, There's no more oxygen down there. Anaerobic, and the methane bubbles out. Yeah. So you get methane from anaerobic decomposition, like landfills, like livestock, all those extra guts that we feed, stuff they can't digest. Our livestock makes a lot of methane. And you get some from changes in land use, like getting rid of wetlands, and a little bit from agriculture. We get our nitrous oxide almost entirely from agriculture. Remember we talked about nitrogen fertilizer and the nitrogen cycle? Ammonia, the ammonification, nitrification, denitrification. In that nitrogen cycle stuff, you get a lot of nitrous oxide. And fluorinated gases, you should know already, we get these from refrigeration and industrial chemistry. Making microchips, a lot of it from microchips, electronics. So anyway, humans are adding greenhouse gases. We talked about that yesterday. I'm sorry this is so scattered. I want to make sure we're tying in all of our loose ends. Oh.
Wait, where do you get N2O from?
Almost entirely from farming, from nitrogen fertilizer. Almost every drop of it comes from, like, the way we till the soil, basically.
Isn't that?
Ask me now, what?
Wait, what's up 3?
O3 is ozone.
Oh.
Yeah.
Would it be possible to put like a factory that like draws up the methane out of the landfill and then burns it for energy?
Yes, and I believe about 8% of downtown Los Angeles electricity comes from methane-powered generators from landfills. I don't think the word is drawing though. I think the word is capturing. But next. Remember what I told you yesterday, that when you add up all the natural factors we know about in climate, the blue bar, you cannot capture recent temperature trends. Nature cannot explain climate. Sorry, recent climate change. Nature can explain a lot of our history of temperature records, but not the last, like 75 years are pretty much impossible to explain with nature alone. But when you combine those human factors, that makes a pretty tidy line. And did I show you all the evidence yesterday?
I think so, yeah.
Be careful, because a lot of people will say, oh, there's no evidence, show me the evidence. Just so you know, there's tons of evidence. Like, the ocean has been heating, sea level has been rising, the planet's been getting hotter, the Arctic has reversed a cooling trend, there's also a loss of ice pack in the Arctic, it's very historic. Greenland has been melting faster, there's less mass in Greenland, the ocean air has stopped. By many different sources, global temperature is rising. Over a very long term, it's definitely risen. And then I talked to you yesterday about science research.
Yes.
Did we talk about how the public sees climate science? And so I'm guessing I left off on this slide yesterday. These are basics that everybody here has to know, because this is the stuff which is utterly indisputable. This is both science, so for your global warming stuff, make sure you have this in your notes. You may have already written this down somewhere and you could highlight them. This is all repeating things I've already lectured on. There are gases that trap heat, the wobbling, stabilizing thing. Those are called greenhouse gases. And because they trap and re-emit heat, that's like the greenhouse. That's the bouncing back heat. That's extra temperature. You know, like closing the windows in your car makes it feel hotter. And just like closing the windows in your car, humans are adding more of the gases. And this is how humans are heating the planet. if anybody can show you how this science is wrong, check their sources, but stay open. What I would recommend to you is, please, let's discuss this science. Show me where this is not accurate. People will argue all sorts of details, but these basics, I'm very skeptical that someone could correct me on these basics. Yeah.
What are their arguments against it?
I mean, most of the arguments I hear are just factually not sound. So there's no way that gases trap heat, or the planet's actually cooling, or the amount of heating we're seeing is all part of a natural cycle. And all those questions have been answered for a long time. People say, show me the evidence. All I'm seeing is a small, like a factor of a half degree. That's not a big deal. But I think that the rational argument, like what the debate you'll have to have with members of your generation, is the value judgment of whether it's worth crippling our economy to deal with this or not. Like how much it's worth spending on this.
Yeah.
I think that's the rational debate. Yeah.
When you say bounce back to the surface, do you mean that they're like in the atmosphere and then they bounce off it? Like how do you bounce back?
Temperature, hotter rises, that's a fact. When that hot air reaches greenhouse gases, it heats those gases, and those gases will eventually cool off by giving the heat back. So technically, Gabby, of 100 degrees that goes into gas, exactly 50 degrees will be emitted back out to space. But the rest of that temperature will come back into the atmosphere, back down. So that's what I mean by bouncing back. You're bouncing back the heat. Like your windows will bounce back the heat from the inside of the car, keep it in the inside of the car. There's a lot of room to argue about the future. We do, however, have some pretty fancy computers, and we have lots and lots of data sources. So the good thing is, while predicting the future is never rock solid, our predictions keep getting better. And there are some things you can say with great clarity. Remember, I've showed you these slides before. Our models are getting more complicated. Our computers are getting smarter. And there just is no good news in the future forecast. Like, I don't know how to pad this for you. The best case scenario is still like historically unprecedented and pretty certainly bad. Like, I don't know if Kobe has 100 good games or 200 good games, but because he's getting older, his game's going downhill overall. And I don't know if we're going to have 10 good years or 20 good years, but overall we're heading into some sketchy years. Yeah?
Will it be their lifetime?
Let me just show you some of the things that we can tell from our current understanding of all the variables that we have available to us. If humans had disappeared in the year 2000, like no new CO2 as of 15 years ago, like right when you were born, if all humanity had stopped and we had zero CO2, we'd have this scenario. Where average global temperatures by 2030 are up about a degree, And by the end of the century, just with that CO2, the year 2000 levels, by the end of the century, global temperatures would be up by like 2 degrees. But that's pretty optimistic because, you know, humans did not disappear in the year 2000. And you probably all know that not only have we made more CO2, but we've grown faster per year every year. So not only is the rate of change positive, but the rate of change is positive.
So it's accelerating.
So we're accelerating CO2 emissions since the year 2000. If we had just kept that rate steady, we would end up with this scenario, where by the year 2030, our planet would probably be in the 1.5 degree, and by the end of the century, our planet would probably be in the 3 to 4 degree range. But it looks now like that was optimistic. Our current predictions are slightly worse than that. In other words, let me show you a different way to look at it. Orange line is if humanity disappeared in the year 2000. So the orange line is keeping the 2000 concentrations of CO2 constant. And the red line is if we keep growing the way we've been growing. And the actual line today is above that because we've increased the rate of CO2 growth. That was never even factored into the data that I showed you so far. See it?
Yes.
And I want to remind you of another unfortunate thing. It's not just the CO2. Like, let's imagine that we just erase all the CO2 somehow. Like, whoop, it's all gone. Like, actually, that doesn't actually fix much. Because of the industrial gases and the methane, like the changes in global food patterns, the fact that more and more people can afford to eat meat, so the livestock thing is happening. Like that we're intensifying agriculture with growing population, the nitrous oxide is intensifying. More and more economies are modernizing, and we have more and more electronics being used around the world, so these are going up. I mean, like, I'm just trying to be honest. Like, you know, if you had cancer, I'd be like, yeah, you know, cancer, this is kind of how cancer works. It's kind of shitty. Like, sorry, like, the climate thing is kind of grim. And there are solutions, and your generation has the power to do that, and they're all, like, tough choices, and you as a group of people leading society any minute now, you'll decide whether we make those choices or we don't. I put a slide in here just as a reminder. Oh yeah, precipitation patterns change. I put a slide in here just as a reminder. Sea level rise has not occurred as fast as we thought it would. That's one of those interesting things about those currents that have sort of surprised us. One of the things that's happened with sea level rise is a lot of the extra water that is on our planet has rained down and been kept on land. We're storing much of the ocean as captured rainfall because dam building has increased. So a lot of that extra ocean volume that we anticipated is no longer being stored in the ocean. We're keeping more and more water in reservoirs on land. So we've slowed the rate of sea level rise from what we initially thought. But sea level rise is another unfortunate prediction where sooner or later we're going to have some fairly significant amounts of sea level rise in your lifetime. Okay. You could also be thoughtful about who you vote for, by the way. Just thought I would mention that when it comes to climate stuff. If you feel freaked out about that, you know. All right. Anybody want to talk more about the climate stuff so far? So then let's move on to number 22. What are positive and negative feedbacks in the climate sense? Like, as a generic concept, what would be positive climate feedback?
Adding CO2 in the atmosphere will heat up the earth.
No, that's climate change. What's positive feedback for climate change? That's one of the details of climate change, but the concept. That's right. That's right. So what would an increase in an increase be? You know, like global warming that leads to more global warming. That's positive feedback. And global warming that leads to less global warming would be negative feedback. Check it out. All of our negative feedbacks rely on albedo. Anybody know what albedo is? Albedo is reflectivity, like how shiny the planet is. So check it out. CO2 might make more plants. Increased rainfall might make more snow. Or increased evaporation might make icy clouds. All of those would cool the planet because the planet gets shinier and more light goes out into space. Those are the negative feedbacks. They all rely on albedo. Anybody want to ask me about those?
Wait, what's albedo again?
Shininess of the planet. What? Reflectivity. Like reflectiveness? Huh?
Luster.
What?
It makes them it's shiny.
Yes, shiny.
How is more plants shinier?
Soil is dark. Plants are waxy. So if you had like a dark brown interior in your car that was kind of a matte finish, and you replaced it with like a waxy light green, your car would probably be a little cooler.
Doesn't the CO2 intake of the plants matter also?
A little bit. But eventually their decomposition, like new plants soak up a bit of new CO2, but in the long term it's not like plants erase CO2. Hey James Bell, put your phone on the house right there. Okay. Negative feedback relies on the albedo of the planet, so more CO2 makes more plants, or more evaporation makes more snow, or more evaporation makes more clouds. And then there are positive feedbacks, most of which cause an increase in the greenhouse effect. Like more evaporation makes swampy clouds, melting of the permafrost releases methane hydrate, or one of my favorites, as the planet gets hotter, people use more air conditioners, which makes the planet hotter, so people use more air conditioners. My friend had a neighbor who lit his garage on fire growing weed. Because inside of his garage, he had a grow room, and when you light up the grow room, it gets really hot. So he attached an air conditioner to the grow room, but it was inside the garage. So by running the air conditioner, he cooled off the grow room and heated the garage, which heated the grow room, which made the air conditioner run. And the guy went on vacation during a pretty hot weekend, and his air conditioner overheated. Yeah, I mean, he did like a crappy job with the electricity and stuff. So not his whole house, not his garage, and somebody called fire department. Great comedy. Great comedy. Yeah.
Did you get charged for the emission of all burned down?
Yeah, I don't know. I don't really know. Like, I just heard the story from a buddy of mine. I wasn't there. And I'd like you to add one. These were all in your book, but I'd like you to add one. Roses. Rain on snow events. Roses. More water vapor, you get more rain. And instead of accumulating snow, you melt away the snow. I'll explain that in a minute, but write down rain on snow events. I'll explain in a second here. In Greenland, you get evaporation, condensation, snow. And every time it snows, you get more ice pack. Then when it's hot, that'll melt away a little bit. Then you get more snow in the winter, more melting in the summer, more snow in the winter. But as winters get hotter, sometimes instead of more snow, you get rain, and the rain washes away the snow. You guys know that water melts ice cubes, right? So as winters become a little warmer, areas that accumulated snow in the past now get what are called rain on snow events. And just a few of those can remove a ton of snowpack. One of the interesting things that you should know, the majority of the South Pole's melting, North Pole's melting, and Greenland melting is not because it's that much hotter. It's just because one or two of the usual precipitation events, just one or two, are coming in rainy instead of snowy. Yeah?
We're supposed to put the road under negative?
It's a positive feedback, because if the planet gets hotter, you get more melting of snow, and that makes the planet hotter because you expose more rock, which traps more heat.
Why does it say under albedo?
It lowers albedo.
Oh, lower, alright. What's that under?
Sorry. Yeah.
Wait, so does it come down as rain since it's
Mine's a little warmer.
Okay.
So it's like erosion for snow.
It is erosion for snow. It's a good way to put it, yeah. If we're done with number 22, I'd like to talk about El Niños, which are number 23. How many of you remember an El Nino year in Santa Barbara? Anybody know what happens during El Nino years in Santa Barbara? What do we get that's unusual? Hot ocean and rain. Everybody know that? What? Yeah, a lot of times, because we get, like more of the jet stream pulling down our way. We get more of those storms coming our way. So yeah. The same storms that bring us the extra rain usually bring us the extra waves. Taylor, relax a little bit. So check this out. I've got normal years and El Nino years. You don't really need this drawing necessarily, but you do need these. This one just helps you understand what this one is. If you have your number 13 drawings, it might be easier to see than my little sketch on the whiteboard. But watch. You remember that in the Pacific Ocean, we have a westerly and a trade, just like in the Atlantic, right? In the northern hemisphere, it spins like this. Did we do that in this class? Remember when we had the Coriolis effect on the paper? I think Luke helped me out. All right. And you remember that in the southern hemisphere, it spins the opposite way. So both the north and the southern hemisphere have a trade wind and thus a trade current right at the equator. Do we agree with that? Is that in your notes somewhere? And if not, can you see that I've drawn those arrows here at the equator? It's critical that you understand how these drawings work because there's going to be a bunch of details, but you need to understand what we're looking at. So imagine this, please. I have rotated my Earth to look at the equator, the Pacific at the equator. I'm going to slice the Earth in half and look at it that way. So you are the South Pole, looking at the Pacific Ocean, with Ecuador on the right and Indonesia on the left. Everybody understand what I'm drawing there? Are we all clear on what this is? Like the center of the Earth would be in here. Yeah? If somebody shoots a rocket into space, it would go like that. Yeah? If there was a boat sailing south, it would come out of the board at you. If there was a boat sailing west, it would go like that. Is this working for everybody? So this is the East Pacific by the Americas, and that's the West Pacific by Asia. Yeah.
On both drawings, like that's America and that's.
Yep. And BT Dubs, that's South America, because we're at the equator here. Now comes the nitty-gritty. Those trade winds, because they're on both sides of the equator, create a trade current that pushes water that way. So you get an equatorial current that goes that way. Surface water at the equator is being pushed that way. If you're in the back, it's difficult to see the red, so please look up. That means the water's getting hotter and hotter toward Indo, and thus you're getting more and more evaporation toward Indo. Because we're pushing surface water over, you know those two trade currents, two trade winds make two trade currents? Everybody agree with me so far? Pushing that hot water over, they get a bunch of evaporation, and please look up. Global trade winds drive an east-west convection current. Do you guys need help back there? Like, I noticed that there's like many challenges for Austin.
I don't have time there.
No, that's cool, sir. But do you guys need help? Are we good? I'm here for you.
No.
No, we could combine this.
Okay. I'm glad to see that. Hot water goes this way, evaporation happens, and you remember those convection currents where you have heat, you're going to make the high pressure, and then you're going to have the opposite cool and dry air mass that falls where everything got pushed that way. In the ocean, likewise, if you're blowing offshore, that's going to make upwelling. So look at the conditions that you get. Normally, Ecuador has cold water and dry air. Cold water from the upwelling, dry air from the other side of the convection current. While Indonesia, they got all the heat. They got a pileup of hot water, and because of the hot water, they also have hot, wet air. If you've ever seen a world atlas, traveled, if you've ever visited Ecuador or heard about it, you might know that Indonesia is one of the hottest and wettest places on the planet, while Ecuador, at the same latitude, is like one of the coolest, driest places on the equator. This is why. Because Ecuador has all the upwelling and all the trade wind.
Isn't this
happen to Indonesia happen to like Brazil?
I imagine that it must, yeah. Although in the Atlantic there may be other factors. The Atlantic is relatively narrow compared to the Pacific. One of the wacky things about the Pacific is this is not drawn to scale. Technically, the Pacific at the equator is almost half the planet. So if I take and show you, here's Indo, right there. Here's Ecuador. I don't know if you can see those, but like that's almost half the planet. So the size of the Pacific means that this water travels a long time before it hits land. And because that water's traveling a long time at the equator, it's heating up a lot. So the normal setup situation is that Asia is way hotter and way wetter than South America. Yeah.
So do El Niños only occur in the Pacific?
The funny thing is that there is actually a very, very subtle Atlantic El Nino, but I think it's only named in the Pacific, and the one that usually drives global weather is the Pacific one. Now, look, El Ninos are a mystery. What stops that nobody understands is you get no trade wind at the equator. A better way to explain that, please look up, is the north and south trade winds spread apart. And as far as I know, that's a mystery. People who understand details should educate you better, but I don't know how to explain the conditions that drive an El Nino. That's why we can't predict them. We can only measure them when they've already started. But an El Nino is the absence of a trade wind, please look up, stops pushing the surface water, so that hot water stays spread out, evaporation is spread out. Instead of giant volume of rain in one place, you get less rain spread out all over. So relative to normal years, that's cooler and drier for Indo, but that's hotter and wetter than the usual on our side of the ocean. So we in Santa Barbara, we experience hotter water and wetter weather because our part of the Pacific has kept more of its moisture instead of having all of that heat shipped over somewhere else. Yeah?
Does El Nino and Indonesia and Ecuador have like more similar climates?
I would suppose so. They have an opposite effect on either side of the ocean. Cooling and drying, heating and wetting. Yeah?
So how dramatic or how noticeable is the temperature difference?
I don't know.
Like,
I've seen satellite images of what the ocean looks like in El Nino versus normal years, and it's regionally very distinct. Where it used to be blue, it's now red, but I don't know if that blue to red spectrum is a ½ degree or 5 degrees. I think it's fairly substantial. I know that Santa Barbara's ocean temperatures in an El Nino are 2 to 5 degrees hotter than the average. And so I would imagine that some parts of the Pacific are even more pronounced than Santa Barbara. Anybody know how to answer that? There's a few other bits of vocab that we have to throw out there. So let's get the vocab, and then we'll be done with this study goal. And I think we'll be done with our day, right? Yeah, we can stop there. Here's a vocab for you. First of all, it's called the El Nino Southerly Oscillation. That means that like heating and cooling of the Pacific is an oscillation. It goes up and down. It follows like a sine wave. So some years are hotter than usual, some years are wetter than usual. Oscillation. El Nino Southerly Oscillation. Next, there's this thing called La Nina, which is the exact opposite. Instead of the ocean being even hotter than normal, it is, on the other hand, even colder than normal. Yeah?
So why is this called El Nino?
It's got something to do with the timing. So when El Niños happen, it has something to do with the Three Kings myth, or the Three Kings story. That Ecuador is a pretty darn Catholic country, and so people there celebrate, like the big Christmas celebration is January 4 or 6 or whatever, when the kings come and they leave gifts in your shoe, not under the tree. And, it's a 6? And that timing corresponds with the shift in weather. So fishermen are like, oh, the baby Jesus brought us warmer water so that we can catch the tuna from shore. Or it correlates to a change in fishing around the new year. And so it is the coming of the baby Jesus, El Nino. The opposite extreme is called La Nina, when instead of getting hotter than usual in the Pacific, it gets colder than usual in the Pacific. And by the way, there is another strange shift in ocean conditions. I'm sorry, because the funny thing is, I don't think you'll need to know these for the rest of your science life, but the College Board has asked all these words often. And so, La Nina, and the last one, the Pacific Decadal Oscillation, the PDO. Pacific Decadal Oscillation. And for the first time in many, many years, I have an Alaskan fisherwoman here. Have you ever heard of the PDO affecting fish in Alaska? Crap. Maybe someday you can think of me if it comes up. Because look, in the north of the Pacific Ocean, there's like a glob of hot water, like a wave in a pool, that slaps against that side and then slaps against this side, and every 10 years it's called the Pacific Decadal Oscillation. So once per decade there's a mass of hot water which moves across and back in the North Pacific. That's all I know about it. And I wish I could give you much of a lesson about it. I know it affects fisheries in Alaska and Siberia. It's got a lot to do with like salmon success and crab success. And I don't know anything else except the College Board has asked about it often. The PDO, Pacific Decadal Oscillation, PDO.
Wait, so the ENSO, is that differences in like the conditions of El Nino when it's happening, or like times?
Oh, ENSO is another name for El Nino.
Oh, okay.
El Nino is the way bros talk about it. ENSO is the way scientists talk about it. Because scientists see this as like a sine wave sort of thing. So it's going to go hotter than normal and cooler than normal.
Is there like an exact pattern to when it will happen?
No, but people are trying to figure out, because it does seem to have like a certain pacing. Like the average gap between El Niños seems to be 4.5 years. But then there's like detail number 1, detail number 2. So we've had a couple back-to-back years and a couple 7-year gaps.
Yeah.
But it seems like 4.5 to 5 is like, yeah.
So for the La Nina, where is it getting colder, or is it just getting colder everywhere?
The surface of the Pacific as an average is colder. So right, like where does all that heat go? Like I don't know I don't know, bro. I don't know, bro. Yeah.
When was the last time you had?
Well, some people thought it was an El Nino at the beginning of this year, and then it seemed to go away, and now people are saying that it's actually an El Nino after all, starting right about now. Has anybody heard this?
Yeah, I heard that. I remember this.
Late El Nino now?
I don't know. I heard on the radio. Wait, how long do they last for?
Usually they're one season, so like 3 to 6 months. Like